Okay, Assalamualaikum and a very good day everyone. In this video, I'm going to briefly explain to you about state minimization in finite state machine. So what is a state minimization? State minimization is a process where the state in the state diagram can be eliminated if any two states are equivalent. Okay, so how to know whether the states are equivalent or not? So two states or two or more states we can say as equivalent if the states have the same outputs and the same next states for the same possible input sequence. Alright, so usually sometimes this can be seen from the state diagram, but to be more exact, this can be seen from the truth table of the FSM. Okay, so this is one of the advantages for Mealy machine, where usually we can do this state minimization. Okay, so when we have this state minimization process, it leads to the less number of states. Alright, so let's move on to the next one. Okay, for example, in this state diagram, we can see that there are so many inputs going to the same output over here V. Okay, and over here we can see it has the same what we call this state same output. Okay, same output. Alright, but from here sometimes we can see whether some of the states are equal or not. But if the state diagram is like this, maybe it's a little bit confusing for us, isn't it? So how to do the state minimization from this state diagram? We convert first this state diagram into its truth table. Okay, so I hope you can try out based on this state diagram, come up with your own truth table and compare the truth table whether it is the same with this truth table or not. Okay, so now let's take a look at how to minimize the states. So from this truth table, we have the present state, input, next state, and output. So over here, we know that two states are equal if the output is the same for the okay, let's recall. Okay, if it has the same output and same next state for the same possible input sequence for the state. Alright, so let's take a look over here. So same output, same next state, and same input for that state. So that kind of what we call a state is called as equivalent if it has the same properties. So we have to compare for all possible inputs. So in this case, if we look at state V has two inputs 0 and 1. So for when the input is 0, the next state is V and the output is 0. When the input is 1, the next state is W and the output is 1. So can we see the other states? Are there any states with the same pattern? So over here we can see the blue colored one over here. Okay, it has the same pattern, isn't it? When the input is 0, the next state is V. Okay, and then the output is 0 as well. And when the input is 1, the next state is W and the output is 1. Okay, so it is observed that these two states are equal. So now we know V and Z are equal. So how about the rest of the states? Are there any states that has the same characteristic as well? Okay, so as we can see over here, if we refer to state W and X, it also has the same pattern, isn't it? Okay, so for both inputs, for all possible inputs. So now we know we have state V and Z that are equivalent, and another set which is state W and X which are equivalent as well. Okay, so when we have this, when we know that there are two states that are equivalent, so we can eliminate one of the states. Okay, for example, we eliminate, because we know V and Z are equal. So let's say we eliminate state Z. Okay, and because we have W and X are equivalent, another set, so we eliminate state X. Okay, so when we do this elimination, okay, kita buang ni, okay, where we eliminate these states. Okay, so we have to refer to the next state written in the one that is left. Okay, so to ensure that it referred to the available state in our truth table, because after this we need to come up with the K-map and also the circuit, right? Okay, so we have to make sure that we have the state that left over here, the state that is available in our truth table. All right. Okay, so that will be the next step. Okay, so the next step is that when we compare, okay, so the states that is available in the truth table now, after we cancel these two states, okay, we can see that over here is written as V, we still have state V, W, we still have state W, Y, we still have state Y, and V, we have state V. How about here, Z? Z we have cancelled just now, isn't it? So we have to put a state name that is available in our truth table, and also the one that is equivalent to the state that we cancel. Okay, so in this case, state Z is equals to state V, isn't it? So here we have to change to V, the state over here. Alright, so when we do that, then only we can move on to the next process, which is come up with our K-map and so on and so forth lah. Alright, so but before we do that, okay, so this is our revised truth table. Okay, our revised truth table with state minimization. Okay, which only has three states. Okay, and then from here we can get our revised state diagram. So see, the state diagram is not as confusing as the first one, isn't it? After we do the state minimization. All right, so let's recall the first version of the state diagram before the state minimization. Okay, so it looks a little bit confusing, right? Because of the too much arrows over here and too many states. Okay, so after the state minimization process, so this is our revised state diagram, where we can use this to proceed with our design. Okay, so with our design, so sometimes we have to do this because for Moore and Milli model FSM, okay, so usually this kind of for this part, usually we will be given problems like this. So we have to read this problem first and come up with the design requirement, and before we can come up with the design requirement, so we have to determine which one is input, which one is output, and the other things as well. And after that, to understand the problem, we have to come up with our first version of our what we call this state diagram. So usually our first version state diagram will look something like this. It will be a little bit messy. So throughout the process, sometimes we need to do state minimization process to clean up our state diagram to become something like this, so that it's easier for us to convert to the right truth table and also come up with the K-map for the equation, and the next one will be come up with the circuit for our FSM. Alright, so I hope from this slide you know how to do the state minimization, and you also have some idea on why state minimization is important for FSM. Okay, alright, thank you everyone for your attention. I hope you get what you should get from this video.